Okay, so now we're recording. PS6 is out and due at the end of the week, as usual. And that'll be it for the first half of the class, for first half of the semester. After that's due next week, we have the midterm on Thursday, so midterm's in like 9 days. I think I posted a sample midterm with the solution. Well, maybe. Anyway, I'm pretty sure a sample midterm is out. Any questions or problems about anything before we proceed? Okay. Yep.
Can you do like one of the last examples on the modular? It's like 135 to the like billionth power, mod 136 or something like that.
So is that a question from the assignment, or?
Yeah, no, it's one of the last questions on one of the quizzes. It's that whole modular quiz.
So it sounds like you want me to do the quiz for you. Is that?
No, I'm saying how do we? Is it? I didn't understand in the slides. There's one that's like 2 to the 345th power, and the way that got simplified, I don't understand how to translate that into doing it in a more generic case.
Okay. Well, let me talk about that that example again.
I think you just had it on that previous slide.
Right.
2 to the 345th.
Okay. Okay, so as it turns out, as we go through this material, we're going to find several ways to simplify seemingly impossible modular expressions. But for the moment, the one way that we have is to realize that it's easy. So if you got some large exponential, if you could convert it into 1 to some power, mod something, then the answer is going to be 1. Okay? And there's one other case that's easy. What's almost as easy as raising 1 to a power? Oh, well, okay, that's even easier. Okay? Well, raising 2 to a power can be tough. I mean, that's a big number. Yeah?
Raising something to 1?
Well, but yeah, raising something to 1 is easy, but to a big power. So 0 to a big power is easy. 1 to a big power is easy, yeah.
Raising the modulo to a power?
Well, raising the base. So let's say it's some number to the 10th power. No, I take that back. It's n to some massive power mod n. What would the answer be? Zero. So if we have n to some massive power taken mod n, how do you know that's 0? Yep.
It's a multiple of n.
Yep, it's a multiple of n. A multiple of anything mod n, a multiple of n mod n is 0. Another way to do it is just to use some of our the properties that we found. So I can rewrite this as n mod n to the giant power mod n. And n mod n is just 0 to some massive power mod n. So that's going to be 0. Okay? But there's one other case that's easy besides that. Yep.
If our modulus is a prime, we can just use Fermat's little theorem.
Well, we'll talk about Fermat's little theorem coming up, and that's another one of the tricks we can use, but we're not there yet. Okay, -1. It's easy to raise -1 to a power. So let's see what I mean by that. So suppose I ask you to take, no, that's not right. -1 to some massive power mod something. All right? What's the answer going to be?
1 or -1?
It's either going to be 1 or -1, depending on what? The parity of this. So if the exponent is even, that means we're multiplying -1 by itself an even number of times, so we'll get 1. Mod n is 1. Or if the exponent is odd, we're going to get -1 mod n. What is -1 mod n? Right, -1 mod n is n minus 1. Just remember, you add multiples of n till you get the number in the right range. Now, having said that, what would be 35 to the 151st power mod 36? How could we simplify that? This is directly related to the trick we just looked at. Yeah.
That would be -1 to the
Okay. What you have to recognize is, again, you can rewrite it as this. You can rewrite it as 35 mod 36. It's just the substitution rule to the 151st power mod 36. This is what? That's just -1. -1 and 35 are the same mod 36. They're 36 apart, so they're the same. So that's the same as -1 to the 151st power mod 36, which is just going to be -1, which then we could rewrite as 35 to put the answer in the right range. So basically, any problem that you see until we learn another technique, where you got to simplify some massive exponential, is going to involve somehow regrouping, simplifying, so that you can get 1 to a power, or 0 to a power, or -1 to a power. All right, so let's just do one more. What about 3 to the 100th power mod mod 26? How can we regroup that using the substitution rule and rules about exponents to make this work? So ideally what you want to have here is 1 to some power, because we know how to deal with that. So yeah.
Can you make it 3 to the 3rd, which is
Okay.
27?
So we could write this as 3 to the 3rd raised to what power? Right? 3 to the 3rd to the 33rd power. That's 3 to the 99th. And then we're going to have to put another 3 here. Mod 26. Okay, now why did I say, where did the idea of using 3 to the 3rd power come from? Yeah.
It's 27, which is only 1 away from 26.
All right, the idea is to get a number that's 1 bigger than the 26. And that's the 27. Now we can use our substitution rule. I'm going to need to make a little more room here. So the substitution rule says that I can say that's equal to 3 mod 26 times 27 mod 26 to the 3rd power, to the 33rd power, all taken mod 26. So I just took the I took mod 26 of 3. I took mod 26 of this. That's all we'll look at that. And so we end up with 3 times 1 mod 26. So the answer is 3. That's sort of the thought process you go through on these. Just remember, you can just take that mod 26, that mod in, and just, you can mod the things you're adding, the thing you're multiplying, or the thing you're raising to a power to simplify it. Any other questions? Yeah?
We briefly covered how to handle negative exponents. Could we go over that?
Okay. Negative exponents, so it's just notation. So if I say 2 to the negative 1, assuming we're working mod 5, for example, I'm asking you, what am I asking you for in that case? What does it mean when I say 2 to the negative 1 power? We're talking about modular arithmetic. Yeah?
2 times what mod 5 equals 0?
You said 2 times,
2 times something. What is that something?
no, okay. That's more like an additive inverse. It is 2 times something, but it's not equal to 0. What's it equal to?
So 2 to the negative 1 is 1 over 2?
Well, the answer is not 1 over 2 because we're working with modular arithmetic, which is just integers. Okay, we're working over integers, so there's no fractions. Yeah.
I think it was 1. I apologize.
Right. So this is equivalent to saying find an x such that 2 times x is the same as 1 mod 5. We're asking for a multiplicative inverse, a modular multiplicative inverse. We're just asking for, when we say this, 2 to the negative 1 mod 5, we're saying what do you multiply 2 by to get 1 if you're working mod 5? All right, so what's the answer to that equation? 3. If we plug 3 in for x, we get 6, and that's the same as 1 if you're working mod 5. Okay, can you think of any other answers? Would 8 work? 8 times 2 is 16. Mod 5, that's 1. So we've got 3, we got 8. What else would work? Yeah?
Just write 3 plus 5k.
Yeah.
K is
Any number of this form. 3 plus, what'd you say?
5k.
5k. So 3, 8, 13, 18, 23, and also negative 2, negative 7, negative 12. Those are all the same. Working mod 5, they're all going to be the same. We prefer 3 as the answer because it's the one between 0 and the modulus. You started to ask a question before, I think.
Yeah. So over here we have 35 mod 36.
Yep.
Give us back negative 1. And would it not normally be 35? Can you choose like when you want
Well,
to be negative or not? Or?
Okay, so when I say right here, over here, where I say 35 mod 36 is negative 1. Yeah, you can, when you're working through it, you could use 35, or negative 1, or negative 37, or whatever suits your pleasure. In our case, negative 1 works better because we can raise negative 1 to a power more easily. Now, when the final answer turned out to be negative 1, at that point, usually I want to see the answer between 0 and the modulus. And so then you change the negative 1 back to 35. But they're just the same thing. They're just different ways of saying the same thing if you're working mod 36. You just have to get used to that. There's an infinite number of integers, but if you're working mod 5, how many different ones are there? 5. 0, 1, 2, 3, and 4. And everything else is equivalent to one of those mod 5. Right? Any other questions? Okay. Now, before we go further with this, I want to say one final thing about graphs. I have a couple points I want to make. And here's the point. You're learning algorithms in this class, and you're learning about graphs or trees or sorting or dynamic programming or linear programming or whatever. But the problem is that you get out and you're writing a program. Problems don't come labeled saying, this is a graph problem that can be solved with breadth-first search, or this is a graph problem that can be solved with Dijkstra's algorithm, or and so on. The hard part about algorithms is not what you're doing in the class, learning particular algorithms. Or it's not even the caddis problems, because they're kind of artificial as well, because I'll tell you what algorithm to use pretty much. The really hard part is recognizing when you can use an algorithm that you know and how to use it. And so what I'm talking about here is what I call graphs in the wild. Graph problems come up all the time, but unless you get some practice, some experience, you may not recognize the graph problems. So the problem I put on the assignment was an example of such a problem. And just to remind you, the problem was you have 3 containers, 10 pints, 7 pints, and 4 pints. The 2 smaller ones are full of water, the largest is empty. And you can do one operation, sequence of these operations. You can pour the contents of one container into another container, but you can only stop when the first container is empty or the second container becomes full. And we want to find the shortest sequence of pourings that leaves 2 pints in either of the 2 smaller containers. So that's easy enough to represent as a graph problem, but you might, right off the bat, you might not have recognized it as such. Okay, so this is you look at that and think, oh, I could use breadth-first search to solve that problem. But you have to be willing and able to figure that out. And you've thought about the problem now. How would you go about implementing it? Suppose you then did recognize, yes, this is a graph problem. I just need to do a breadth-first search. I need to think of this as a graph in a certain way and then do a breadth-first search on it. How would you go about implementing it? You all did breadth-first search last week on the caddis problem, so that's not novel. So what would be the steps? Yeah?
Well, you have to know what each vertex in the graph represents.
Okay, so you've got to have a good idea of what kind of graph you're after. Okay? So this is the solution I had in mind. We'll let the vertices of the graph represent a state of all the containers. And so we have a vertex, for example, that represents the situation where the first container has 0 pints, the second container has 7 pints, and the third container has 4 pints. So those are the vertices. Then what are the edges? When is there an edge between 2 vertices? A directed edge. Like in this picture, why is there an edge from 0, 7, 4 to 7, 0?
Because you can.
Yeah.
It represents one pour.
Yeah, it represents a legal pouring. So for example, I think this must be large, medium, small. So if we take all of the medium container and pour it into the large container, you get to this state where there's 7 pints in the large one, 0 in the medium one, and 4 in the small one. That's a legal pouring. So we put an edge in this direction. Now, why do I have it bidirectional? Well, I could just turn around and pour this into that and get back at 0, 7, 4. On the other hand, this state where there's 4, 7, 0, and I go down here and end up with 10, 1, 0. So I poured 6 of the 7 pints from the medium container into the large container, ended up with it full, 1 pint and 0 pints. Why is there not an edge back?
Couldn't you do that?
Okay. You cannot edge back because I made a mistake, is that right?
Yeah, you put that 10 back into the 7, and you get the 6 back.
All right. Okay, never mind that. Sometimes you can't go back. Sometimes it's not necessarily both ways. So anyway, you have a directed graph. And the question we have to ask is, you got to do a breadth-first search for a vertex of the form, well, you're doing a breadth-first search starting with the initial state, which is that the initial state? I don't remember.
Yeah.
Anyway, you're trying to end up in a state of one of these forms here that has 2 pints in either the small or the medium. Okay? So now you've got it all figured out. What's next? How do you implement it? You can describe it as a graph problem. You can draw the graph. You can think, oh, I've just got to do a breadth first search. How would you code it up? Yeah.
For any given node, you just have to generate the valid pores from there and have a visited
Okay.
sort of way.
So, all right. So he said an interesting thing. He said for any valid node, you have to generate the neighbors, basically. So the point I'm trying to make, and that helps with making the point, is do you construct the graph and then search it? No. Think about a program that plays chess. Okay? Can you view chess as a graph problem? What would each vertex correspond to? A position on the board. And then the edges would correspond to legal moves between positions. Right? And there, definitely, sometimes you can go from position and back to it, but if it's a capture or a pawn move or something, you only go in one direction. All right. And so we could describe the problem of playing chess as a problem of searching this graph in some fashion. So suppose you could do that. Would the first step then be to construct a graph of all legal positions? It'd be too large. It'd take forever. Well, it wouldn't take forever, but it would take a very long time to construct a graph of all legal positions. What you would do is generate the graph as you searched it. Now, think about Google. Google views the web as a large graph, and it searches the graph. Does it first create a model of the internet on some gigantic server and create a graph representation on some gigantic server and then search it using one of our algorithms? Does it first generate the entire graph and then search it? No. It just goes out and visits vertices on the graph on the web, which are web pages, and then searches out from there. It generates the graph as it searches. And that's very common in graph problems. So a lot of times when you write a graph algorithm, you don't build the graph completely and then search it. Now, what you did on Caddis, that's how you did it, because the graph was just given to you. But a lot of times you start with one vertex, and you start your algorithm, and when you need to know what the neighboring vertices are, you generate them on the fly. So I just want to drive that home, I want to show you a simple Java program that does that. So here's a Java program. Here's how I represent the state. I just have three instance variables that say how much water is in each of the three containers. I have a constructor to create the initial state or a specific state. And here I have something that, given a state, will return the list of all reachable states from it. And it just goes through and applies the rules of pouring, and comes up with between 0 and, I think there's 6 possible. There could be as many as 6 neighbors. So this, you get a vertex, which is just a triple of numbers, and it tells you the list of all neighboring states you could get to. So that's the graph. And then here's the algorithm. Let's look at breadth first search down here. So we got this breadth first search algorithm that has a start state, and then it has a previous map, previous array, like we did with breadth first search. And it is straightforward breadth first search. It starts by putting, making the previous of start be itself to mark it as the top, as the start. It creates an empty queue. It adds start to the queue. While the queue is not empty, it removes something from the queue. Then, for every neighboring state, if we haven't been there, we add it to the queue, update the previous array, and check to see if we've reached the end. This check to see if we've reached the final state that a final state that we care about is really the only tweak that I've made to breadth first searching. The point to realize is we're not looking up the neighboring vertices in a static data structure. In this for loop, we are just calling. We got a state S, we want to know its neighbors, so we just call the next states method and we get back a list. So it's being generated on the fly. Most of the graph the whole graph would be fairly large. Most of it's not even generated when you're searching it. Just the vertices that matter are created and searched. Yeah?
I know we haven't really covered this yet, but how does this affect like graph, like path reconstruction if you're generating a graph dynamically?
Okay. So path reconstruction. So the result of this is going to be null if we did not find a final state. If we did the search and we did not find a final state, the answer is null. Otherwise, it's going to return with the final state that it found. So what's it going to take to reconstruct the path? Right? We just go to the previous array. We start with this state. We see who its parent is. And we walk our way back to the original start state. And that code is sitting right here, where it says print out the path from the root to the final state. So it creates a linked list of states. It adds S, which is the final state that we found. And then it just works backwards in the previous array, finding parent, 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 until it gets back to the original root. Yeah?
So that generate neighbors method that you have, does it check to not like create states that have already been created? Because I see this just going on forever and ever. I don't see how
No, it doesn't. It isn't checking to see that it hasn't created a state before. But how do we avoid that? Why is that not a problem with VSOLVE here? How do we avoid searching things that we have already searched? The traditional array and vector search is you have a visited set, right? You don't visit something twice. How do I avoid visiting twice here? I don't have a visited. Yeah?
If you're not shot for your previous result is found, and there you know you visited it.
Right. So if R has a previous, then we don't search it again. We've already searched it. So this prevents us. So we may find a vertex that we've been to before, but we throw it away immediately. We don't search out of it. Question back there. And I have an example here also of depth first search. I won't go into the same idea. Depth first search will tell you, is there a way to get there? It won't tell you how to get there or what the shortest way is. Yeah?
And that prevents it from having two parents, right? Because it'll go
Right.
down one and the other one will just say, I can't.
Right. Yeah, the previous array, you want something to have a unique parent.
Yeah.
Yeah. The previous array encodes the shortest path from the start to every other vertex that you've reached. In particular, the shortest path to a vertex that has a 2 in either the second or the third spot. Now, what if we change the problem so that you had to pay for each porting? And the amount you had to pay depended on some complicated price formula that depended on the amount of water in each container. What would have to change about this? Yeah?
Can you just change it to a priority queue and use extras?
Yeah, so we'd use Dijkstra's algorithm instead. Right? It'd be more than just using a priority queue. We'd have to change how we update the data structure, but yeah, you just use Dijkstra's algorithm. But again, you generate the graph as you go. Yeah?
Just a question. So we're talking about how with the priority queue,
Mhm.
we want it to be a certain time depending on what type of graph we're using. What is Java's priority queue? Is it better used for it to list
I'm virtually certain Java's priority queue is a binary heap. Yeah. But the problem, I mentioned this in the current catus problem. The problem with Java's priority queue, and also with maybe C# or C++, I don't remember which, is the update operation is linear. And if you need to use an update operation, and the linear update operation will kill you on time. So I'm not saying not to use, I give a suggestion on how to work around that. But it avoids not using the update operation. But do keep that in mind. Any other questions? Okay. Okay, now this is the slide that we ended with last time, so I'm just going to review what we talked about. We talked about doing modular addition and multiplication. And what we found was, okay, the game we're playing is you've got two numbers, x and y, that are between 0 and n, where n is the modulus we're using. So to add x and y mod n, you just add them normally, and if the sum is too big, i.e. if it's greater than or equal to n, you just subtract n off. So at worst, it takes an addition and a subtraction. The amount of work is proportional to the length of the numbers you're working on. Now, if n is the modulus, what is the length of the numbers you're adding? What is the measure of the number of bits? An upper bound of the number of bits in two numbers if you're working mod n. Right? Suppose n is a million. What's the most bits that x and y can contain? You know x is no greater than n. Yeah?
Log 2 of a million.
Log 2 of a million, which is about 20. Okay? So that's why you see log n in the complexity here. We say the complexity of addition is O of log n because the time depends on not the magnitude of numbers, it depends on the length of the numbers. And you know that. When you do long addition, if you're adding two 3-digit numbers using long addition, that takes a certain amount of time. If you make them twice as long, it takes twice as long for you to add. So it's linear, but it's linear in the length of the numbers. N is a measure of the magnitude. Log n is a measure of the length. The number of digits, the number of bits is the log. So that's why we express it that way. With multiplications, you have to do the multiplication and then do a modular. You have to do a division to get the remainder. And that division is quadratic, so you get log squared of n. And you know that too. You do a 3 by 3 multiply, and then you change that to a 6 by 6 multiply. Is that just twice as hard? No. You know that's more than twice as hard. It's like 4 times as hard if you use grade school multiplication. Now, typically, if we're using big N as the modulus, we're going to use little n to stand for the log of the modulus. In other words, little n is going to be the number of bits, the number of digits, what have you. And so we can also say, in that case, we can say addition is O of n, modulus O of n squared, where little n is the number of bits. But typically, we want to express complexities in terms of the size of, amount of memory taken. That's why I'm working to make this distinction here. It becomes increasingly important as we go along. So that's addition, multiplication, all pretty easy. Now let's talk about modular exponentiation. So here the problem is, you're given 3 numbers, x, y, and n. N is the modulus. X and y are between 0 and n. We want to compute x to the y power mod n. Now you may be wondering, why would you ever want to, why is that an interesting problem? And here's the answer. Public key encryption, which is the basis of e-commerce, the encryption step is that. Your message, the thing you want to send, your credit card number, if you will, is x. There's a key, which consists of y and n, and the way you encrypt is, you take the message, raise it to the power y, and then take the result mod n, and that's the encrypted version of the message. And decryption is the same way, but with a different exponent. So modular exponentiation is at the heart of e-commerce. So it's important to know how to do it efficiently. So I'm going to look at 3 approaches. The simplest one I can think of is start with x, multiply it by itself, y minus 1 times, and then take the result mod n. Okay? So for example, if we want to take 4 to the 5th power mod 7, we could do 4 times 4 times 4 times 4 times 4. That's 1024. We take that mod 7, which would be a division, and we note the remainder, which is 2. So what do you think of that technique? It's going to take a while, especially if x and y and n have a lot of bits. Now in public key encryption, n might have 2048 bits. So x and y could be numbers with 2048 bits, which is like about 800 digits. So imagine an 800-digit number raised to an 800-digit power. And you do this by multiplying this 800-digit number by itself over and over and over again. It would take a long time, and the number will get gigantic before you take the mod, right? So that's not how it's done. But let's see how bad that is. All right, that first operation we're going to let little n be the length of big N. We do n squared operations. The result has 2 n bits. So we're multiplying an n bit number by itself. So that's going to take n squared time, and the result will be twice as long as the original one, right? So our next multiplication is we're multiplying an n bit number, x, by a 2 n bit number, x times x. So how many operations is that going to take? How much worse is it? So the first line we multiply n bit number by n bit number, and that took n squared operations. Is it worse to multiply a 2 n bit number by an n bit number? How much worse? Yes, twice as hard, twice as many steps. So you end up with 2 n squared operations with a 3 n bit result. And then the next step, you'll do 3 n squared operations and have a 4 n bit result. And the final one, you'll have a y minus 1 times n squared operations, and the result will have y n bits. Okay? So let's focus on that number, y minus 1 times n squared. Let's add all the numbers up. N squared plus 2n squared plus 3n squared up to y minus 1n squared. What's the answer? It's n squared times the sum 1 plus 2 plus 3 up to y minus 1, right? So what's that sum in the, right in here? What's the sum of the first y minus 1 integers? Yeah, y times y minus 1 over 2. That's our familiar formula. So this is a lower bound on the cost of the algorithm. So the sum of that sum of from 1 to y minus 1 is roughly y squared times the n squared. But what's y squared? We got to express y squared in terms of little n. What's y in terms of little n? Now, where'd that come from? I'm equating y with 2 to the n. Yeah?
That's how many bits are in y?
Well, I know how many bits are in y, that's n. Yeah?
Your architecture is some power of 2.
No, it's not. It has nothing to do with the architecture.
Or 2 bits.
Let's suppose y is 1,000,000. Okay? What would little n be? How many bits in 1,000,000?
About 20.
About 20. Log base 2 of 1,000,000 is 20. And so if we wanted to express y in terms of the number of bits in it, what is it? 2 to the number of bits, 2 to the n. Roughly speaking, n is log y. So that means 2 to the n is equal to y. So all I did was replace y by 2 to the n. Right? Y is n is the log of y, and so we recover, 2 to the n is equal to y. Anyway, that works out to at least 4 to the nth power times n squared operations, and we haven't even discussed the division that would be required at this point. So we get this massive number why n bits long takes, exponential time to do it, and then we still have to do a division. So e-commerce wouldn't work if that's what we had to do. What would be a better way? Let me frame the problem a little better first. One problem is the numbers keep getting bigger and bigger. Yeah, there's a lot of multiplications to do, but also these numbers keep getting bigger and bigger. What can we do about that? Yeah.
Can you take the mod at each step?
Yes. What we did here was we multiplied, got this gigantically long number, and then we take the modulus. It's going to be a massive division. And one reason the complexity mounted up was each successive multiplication took longer and longer because the numbers became longer and longer. We can use the substitution rule, and after each multiplication, take the mod. Knock it back down to size. Then do another multiplication. Then take the mod. So the numbers never get very long. You're going to take the mod at the end, so why not take the mod as you're going? So let's see here. We're going to take the mod after each multiplication. Let's see an example. 4 to the 5th mod 7. So first we do 4 times 4, which is 16. We take that mod 7, we get 2. What will be the next multiplication to do? 2 times 4 mod 7 is 8, which mod 7 is 1. Then we do 1 times 4, which is 4. We take that mod 7, we get 4. And then we do 4 times 4 mod 7, which is 16 mod 7, we get 2. And that's our answer. So rather than do 4 times 4 times 4 times 4 times 4, and then take it mod 7, we just take the mods as we go along. It keeps our things more, our numbers more smaller. Let's see. Well, before I even do this, is this going to improve on our previous complexity bound?
Yes.
Okay? Is it going to reduce the number of multiplications we have to do? And before, we had to do an exponential number of multiplications. It's still going to require an exponential number of multiplications. It's just each multiplication is cheaper. So each step, we have to do a multiplication and a division of n-bit numbers. So that's the n squared. And we have to do y minus 1 of those steps. So we don't have to do that sum anymore because each step is the same complexity because of the mod. And that's just 2 to the n squared. So before we had 4 to the n squared, this is 2 to the n squared. This is a lot better, but still not practical. That 2 to the n is just too large of a number. N is, if n is even 100, the number is too big to think about. Okay, well, we're on the right track though. We never have to deal with more than n bits. All right, here's the third way. Can you think of a way to compute 4 to the 8th mod 7 without doing 7 multiplications? Yeah.
Can you figure out what the mod would be for each positive and each even and odd power, and then maybe figure out if you multiply it so many times what the remainder would be?
We might could think about doing that, but there's actually, for this particular problem, there's a very direct approach I have in mind. Yeah?
Do we take it, do we make 48 to the 16th, and then we can turn that into 2 to the 3rd?
Okay, you're trying to simplify it using the techniques we talked about at the beginning of the class, right?
Yeah.
Yeah, and there may be a way to do that, but there's a general in this case I want to take advantage of the exponents of power of 2. Yes. Yeah.
Oh, me?
Yeah.
Like successive squaring. So we do 4 squared. We know that it'll be 16, and we'll know that's 2. So then we can take 4 squared times 4 squared, 4 to the 4th, but that's just 2 squared.
Exactly. All we have to do is view it this way. X to the 8th is x squared, squared, squared. Let's just do repeated squaring. And furthermore, after each squaring, we can take the mod to keep the numbers from getting out of hand. So first thing we'll do is 4 squared mod 7, which is 16, which mod 7 is 2. So what's our next operation going to be? We square the 2, right? 2 squared mod 7 is 4, and now we square the 4. 4 squared mod 7 is 2. We got the answer. We only had to do 3 operations. Well, that's great if all our exponents are powers of 2. But they don't come that way. We're going to use a divide and conquer algorithm, and here it is. So we're given x and y, and the assumption is x and y are between 0 and n. We want to compute x to the yth power mod n. Now, if y is 0, the answer is 1, and we're done. Otherwise, what are we doing? What does this recursive call do? We're dividing y in half and taking the modular exponentiation of x to the y over 2 power mod n. Yes?
Even you're doing this algorithm that is odd, you're doing the previous.
Okay, if y happens to be even, let's say y is 6. We're going to compute x to the 3rd mod n, and then we're just going to square what we get back, which will give us x to the 6th, and we take that mod n. But what if y is odd, like 7? Well, in that case, again, we compute x cubed mod n. Then down here, we square it to get x to the 6th, and then we multiply by an extra x to get x to the 7th. So it just depends on the parity of the exponent. You divide the exponent in half, make the recursive call, and then reassemble. So I think I have an example out here on the side somewhere. So 4 to the 5th mod 7 again. So what's the recursive call going to be? So using this technique, if you want 4 to the 5th mod 7, the recursive call is going to be what? 4 squared mod 7. We just divide the exponent by half and discard any remainder. So we will do, so there's the call. Mod exponentiation of 457. We're going to call mod x of 427. All right, there's mod x of 427. What recursive call are we going to make for it? 417. Again, divide the exponent in half. Now we're there. Mod x of 417. What's the recursive call going to be? We could call that a base case, but I don't believe I did there.
407.
Right, we divide the 1 by 2, we get 0. So we do mod exponentiation of 407. Now what's the answer to that? The answer is 1, because that's the base case. So now let's just go back up the stack here. The answer here was 1, so z here is 1. What are we going to do with the 1?
Square it.
Our exponent was odd, so that says we're going to square it and do what? Multiply by 4. So we square the 1, multiply by 4, take the mod 7, we get a 4. Okay? So z up here is 4. What are we going to do with it? Square it mod 7. We get 2. Now we're back up to here. The exponent was odd. Z is 2. So what do we do? Square it, multiply by 4. Mod 7 is 2. And that's our answer. So that's modular exponentiation. Yes?
This isn't directly related to this,
Mhm.
but how worthwhile would it be to use dynamic programming on a problem like this?
Okay, so what you're observing is that we kept computing the same thing. We computed the same thing multiple times, right? So if you could,
But like when it gets to really big numbers, is it
Yeah.
still useful?
I think, so when he's talking about dynamic programming, essentially we could pre-compute, so we ended up doing 4 times 2 squared mod 7 twice. So you could imagine having a table that just stored, okay, if you're doing 4 to the 2nd power mod 7, here's the answer pre-computed. That would be dynamic programming. The table would just be too big for logging in.
Okay.
It's quicker just to compute it. What's the complexity of this look like? How many steps do we have to do? We could apply the master theorem here, but let's just analyze it a different way. How many times can you divide y by 2 before you hit the base case? by y, right? Which is little n. So there are little n steps. How expensive is each step? Each step is at most 2 multiplications and a division of n-bit numbers. So what does that cost to do? 2 multiplications and a division where the numbers are all n bits. Well, now, how much is 1 multiplication with n bits? N squared if you use grade school algorithm, and the division is n squared, whether or not we use grade school. So you've got 3 n squared operations, and you do that n times. So it's an n cubed algorithm, where n is the length of the modulus. And it turns out that n cubed algorithm is a bottleneck in public key encryption, and is one reason why as computers get faster, we have to use longer and longer numbers for public key encryption. We'll talk more about this later. I'm just giving you a preview. And as a result, the time to encrypt becomes longer and longer, really fast. And eventually we'll get to a point where it's just not usable anymore. Have to do something different. But that's a story for a different day. Let's take a break and we'll look at some more algorithms. I got into the wrong spot here. Hold on a second. Still in the wrong spot. Okay. This is what we just talked about. So on the left, upper left, you have the recursive algorithm for modular exponentiation we talked about. On the right side is an equivalent algorithm, except it's iterative. And you can, if you look at the if and the else in there, you can see we're doing the same operations. Sometimes we do x times z squared mod n, sometimes we do z squared mod n. And it's all controlled by the bits in the exponent. So we look at the bits in the exponent from the high order bit to the low order bit, and use that bit to determine which operation you do. Do we square and multiply, or do you just square? And it works out to be the same. You can verify if you want to. So it's not, you don't have to make it recursive. And either way, you've got an n-cubed algorithm. All right, so I mentioned that's a key algorithm for encryption. That's how encryption is, public key encryption is done, and public key decryption. But another thing we have to figure out is, where do these keys come from? When you're doing the encryption, where do the exponents and the moduli come from? And that requires some more algorithms on large numbers. So that's what we'll continue looking here. And one of the algorithms that you have to use when you generate keys for public key encryption is greatest common divisor, again, on arbitrarily long integers. And I think that's pretty cool, because the algorithm for greatest common divisor is like 2,500 years old. And yet it has an application here in one of our key technologies. So let's see how that works. So the greatest common divisor of two integers is the largest integer d that divides them both. So let's just make sure we're all familiar with the concept. What's the GCD of 14 and 6? Okay, so 2 is the largest one that divides both of them evenly. What about 50 and 17? 1. They've got no factors in common except 1. 17 being prime. 50 is not a multiple of 17. What about 12 and 20? Yeah, 4. So how are you doing this in your head? Yeah, you're just sort of thinking about the factors. You say, oh, they're both even, but oh wait, 4 works, but no, 5 won't work. Yeah, you slowly come to the realization what it is. All right, so this is Euclid's algorithm. Actually, Euclid didn't express it this way. He expressed it in terms of dividing as opposed to moduli, but this works faster. If b is 0, you return a. Why does that make sense? Why is the GCD of a and b going to be a if b is 0? Yeah, anything will divide 0, and so the biggest thing to divide a is itself. Otherwise, we take the GCD of b and a mod b. So let's do GCD of 14 and 6. So we're not down to 0 yet, and so the first argument becomes 6, and the second argument becomes 14 mod 6, which is what? Yeah, 2. So it becomes GCD of 6 and 2. So the thing to realize is the second parameter becomes the first parameter, and then the new second parameter is the modulus of the original 2. I mean a mod b. Okay? Now what's the next step going to be? It's going to be GCD of 2 and 6 mod 2, which is what? 0. And that's our base case. So there you go. What about 50 and 17? Ooh, it's a little harder to do in your head, but anyway, it's the GCD of 17 and 16, which is going to be what? 16 and 1, modulus of 17 and 16. 17 mod 16 is 1. GCD, that's going to be 1 and 0, and so the answer is 1. 12 and 20 becomes 20 and 12. That's sort of a property. If the first parameter is less than the second parameter, then the first step is just to put them in a different order. This is how it works out. That becomes 12 and 8. That becomes 8 and 4. That becomes 4 and 0. So the answer is 4. So the algorithm is pretty straightforward. Do we have to do anything different if our integers become large? I mean, obviously, the algorithm that we had for exponentiation didn't work at all when integers became large. They just became too slow. But what operations are we doing here? Each step, what does it take? Yeah, just a mod, a division. So for large numbers, we just have to do a division at each step, and furthermore, the numbers get smaller and smaller as you go. So it doesn't really take any special algorithm to do it. And here we have on the left, we have what we just looked at. On the right, it's easy enough to turn it to an iterative algorithm. So either way works. Now, here is Euclid's rule, his original rule that he used to justify the algorithm. Was he said if x and y are positive integers with x greater than or equal to y, then the greatest common divisor of x and y is equal to the greatest common divisor of x minus y and y. Okay? Now, he was using subtraction instead of modulus. But why is that? So where does a modulus come from? What does modulus have to do with subtraction? Yeah. It's just right. To take a modulus, one way to do it is to do multiple subtractions until you get the number small enough. You subtract the modulus over and over again until you get small enough. Rather than do a whole bunch of subtractions, which Euclid would have done, we're just doing a modulus, which does it in one step. So let's see if we can prove Euclid's rule. So first, we want to show those two sides are equal. So it says here, if d divides both x and y, it must also divide x minus y and y. So why is that true? Well, let's take it. D divides both x and y. So why must it also divide x minus y? Yeah?
So if it divides x minus y, then x has to be some multiple of y, and then removing y from it still keeps it a multiple of y.
Okay, so let me see if I can paraphrase that. If d divides x and y, well, okay. If d divides x and d divides y, what does the difference between x and y have to be? A multiple of d. And d is going to divide a multiple of d. And clearly, if d divides y, it'll divide y. So that's good enough. And we can conclude from that that the GCD of x and y is less than or equal to the GCD of x minus y and y. Now, where does that come from? That can be a little confusing. What justifies that? The first thing, the fact about d up there, justifies the second thing. You got an idea? Euclid figured it out. All right, so I'll admit that there have been times in the past when I had to stop lecture and have someone explain it to me before I could explain it to the class, because it just slipped in my mind about the explanation. But I actually looked at the slides before class this time. All right, so here's the idea. Let d be, I want to pick a number d that divides both x and y. Well, what about the GCD of x and y? Does that divide both x and y? Yeah. So let's call that number, let d be the GCD of x and y. So since it divides both x and y, it divides both x minus y and y, according to the previous slide, right? So that d here is a divisor of both x minus y and y. Okay? What does that mean? It's got to be less than or equal to the GCD of x minus y and y. We know that this divides x minus y. So the GCD of x and y divides x minus y. The GCD of x and y divides y. So the GCD of x and y is a common divisor of x minus y and y. You see that? But this is the greatest common divisor. So this GCD of x and y can't be, it's a divisor, but it's a common divisor. It can't be bigger than the greatest common divisor, so it has to be less than or equal to it. That's the thing in a nutshell. It's not complicated. It's just easy to get lost in the GCD notation. Okay, and if we and then the rest of the proof is exactly the same argument, just turned around. You can show that the GCD of x and y is greater or equal to the GCD of x minus y and y, so they have to be the same. So it's it's a neat little argument. It's 2,500 years old. It's worth seeing once. So now you've seen it. Okay, now let's go to the complexity of the GCD algorithm. Let's see how bad that is. Now here's my observation. I claim that if A is greater than or equal to B, then A mod B is less than A divided by 2. I want you to think about that for a second. Do you believe it? So let's take 7 and 3. 7 is greater than or equal to 3. Is 7 mod 3 less than 7 divided by 2? What is 7 mod 3? 1. And that's less than half of A. Right? So it worked out there. Why does it work out? Yeah?
The smallest integer divisor you can have is 2. So like 2 will at most be dividing by 2.
Okay. So he's looking at that divide by 2 and making an argument about the smallest integer divisor. That's a good way to look at it. Let me put it a different way. Suppose that A and B are really close to each other. Let's say A is 1 billion and B is 1 less than it. So suppose B is really close to A. What's A mod B going to be? 1, or really small. So if the A and B are close together, the modulus is going to be really small. Now, what if A is giant and B is tiny? What can you say about the modulus?
It's going to be at least smaller than the modulus.
It's got to be smaller than B. But again, it's going to be tiny. So it just works out that either B is giant, if B is big, then the modulus is just the difference between the two and it'll be small. Or if B is small, the modulus is going to be less than B and it'll still be small. And it's when you're sort of in the middle that you get the largest A mod B is the largest. So just to work this all out, if we suppose B is small, in that case I mean less than or equal to A divided by 2, then we know that A mod B is less than B. Okay? Which we're assuming is less than or equal to A divided by 2. So we get A mod B is less than B because it has to be less than B. And B is less than or equal to A divided by 2. So we get A mod B less than or equal to A divided by 2. That's the case where B is small. And the other case is the case where B is large. So suppose B is greater than A divided by 2. In that case, A mod B is just A minus B. And that's going to be less than A divided by 2. So how can we use this fact? That when A is greater than or equal to B, A mod B is half of A. How can we use that to our advantage to prove this thing? Where does A mod B show up in Euclid's algorithm? Yeah, it shows up right here. Okay? So what that means is you take the GCD of A and B. Let's start out by assuming A is greater than B. You take the GCD of A and B. In the recursive call, you've got A mod B, which is half the size of that A, right? At most. Now, what's going to happen to this A mod B in the next step? Right now, A mod B is the second parameter. What will happen to it when we make this recursive call? It'll become the first parameter. So that means that if you looked at the sequence, you would see A at the first stop, at the top, and then there would be a step, and then you would have A mod B. So every other time in the recursion, the first parameter is being replaced by something at most half its size. And that repeats over and over again. So that puts a limit to the depth of the recursion. So at most every repetition, A will be halved, is what we're saying, because we start with AB, the next time we have A mod B as a second parameter, and the time after that, that A mod B becomes the first parameter. Okay? At most every other repetition, A will be halved. If A and B are n-bit integers, they'll be at most 2 n repetitions, because we're cutting something in half. We're cutting the original A in half each time, every other time. Each repetition is n squared because there's a division involved. So that would seem to say that GCP is an n cubed algorithm, O of n cubed. Now, turns out it's n squared. So yes, it's O of n cubed, but it's also O of n squared. Where did the overestimate come from? Yeah.
N's getting smaller.
Okay.
So that n squared on each repetition is getting smaller as we're repeating more.
Right. One thing to notice is n is getting smaller with each repetition. The numbers are getting shorter with each repetition. And so the cost of the mod is getting cheaper and cheaper because the numbers keep getting smaller and smaller. So we sort of assume the worst case, that each mod operation would be the same n squared cost. So the length of the numbers gets shorter and shorter. What would be another source of overestimate here? Yeah?
Assuming that those 200 repetitions are done every time.
Okay, so it has to do with the repetition. So we were assuming that every other step, A was cut in half. And that's a worst case as well. It could be cut in more than half. And it won't necessarily take two steps for it to happen. That was just an upper bound. It turns out that in practice, you get an n squared operation. So this just summarizes what we just talked about. So in n-bit numbers, Euclid's algorithm is quadratic. And it turns out it's kind of neat. The worst case is for consecutive Fibonacci numbers. So the worst case for GCD is when you feed it consecutive Fibonacci numbers. So remember that the first Fibonacci number is 1, the second one is 1, and the kth one is the sum of the two that came before it. So let's see this. What's the GCD of the kth Fibonacci number and the k minus 1th Fibonacci number? Okay. Apply the algorithm here. Look at the recursive algorithm. What's the next step? If you had to take GCD of f sub k and f sub k minus 1. Well, in the recursive call, what will the first parameter be? Look at the code up there. Yeah. F of k minus 1, comma, okay, fk mod fk minus 1. Okay, what's that going to be? Fk minus 2. Okay, let's think about why that is. F of k, is f of k minus 1 more than half of f sub k? Remember, f sub k is just the sum of f sub k minus 1 and f sub k minus 2. F sub k minus 2 is the smaller, and so f sub k minus 1 is more than half. So how do you compute the modulus of two things, of a and b, if b is more than half of a? You just do a subtraction. And if you subtract f sub k from f sub k minus 1, you get f sub k minus 2 by the definition of okay, so we got f sub k, it becomes that, it becomes that. Okay, so there's the long justification that we go from f sub k minus, f sub k of GCD of f sub k and f sub k minus 1 is equal to the GCD of f sub k minus 1, f sub k minus 2. And you can see where this is leading. Eventually, we'll get down to the GCD of the first two Fibonacci numbers, which is just 1. So it turns out the GCD of any two consecutive Fibonacci numbers is 1, and Euclid's algorithm finds that fact out. but it turns out to be the worst case it's the worst two numbers you can feed of a given size to GCD. You get in terms of its complexity. All right, so we're going to spend the last 5 minutes on what I spent the last 5 minutes on last time, which is modular multiplicative inverse. And we actually started today with this. So we say that x is the multiplicative inverse of a mod n when a times x is congruent to 1 mod n. So let's do some examples here. What's the inverse of 2 mod 3? I think we already did that. Well, maybe we didn't. What can you multiply 2 by to get 1 mod 3? 2. 2 times 2 is 4. 4 mod 3 is 1. Okay? So a number can be its own inverse. What's the inverse of 4 mod 7? 2. So what you're looking for in these problems is you're looking for a multiple of 4 that's one more than a multiple of 7. And so I sort of go, okay, I need to get something that's one more than a multiple of 7. Does 8 work? Yeah. 2 times 4 is 8. Now, this won't be an issue on the midterm, but on the final, there'll be a problem like this where you've got to compute a modular multiplicative inverse. And we're going to study an algorithm next time for doing it. The algorithm's complicated. I've never succeeded in running it in my head right, ever, the first try. It's not that it's like intellectually complicated. It's just a lot of record keeping. It's tedious. But you can always solve these in your head. That's what I have in mind when I put them on the exam. It's just, do you know what a modular multiplicative inverse is? And it always pains me when I see students actually in the exam working through that algorithm very laboriously. Probably the first time they've done so, trying to get the answer that they could do in 5 seconds in their head. Okay? What's the inverse of 5 mod 8? It's taking you a little longer. Yeah, 5. Again, I'm looking for a multiple of 5 that's one more than a multiple of 8. So, yeah, 9 ain't going to work. 17, but 8 times 3, 24. Yeah. 25 mod 8 is 1. That's sort of what I think. So 5 times 5 is 25. 25 mod 8 is 1. So it's 5. I mean, how many possibilities are there? If I ask you for the inverse of 5 mod 8, how many numbers do you have to check to multiply 5 by? 8. Well, right, there are only 8 distinct numbers, mod 8, 0 through 7. 0, you know, is not going to work. 1's not going to work. Unless you're taking the inverse of 1. Yeah?
What would be the answer if you were given a number that didn't have a multiplicative inverse?
Okay. We'll get there. What's the inverse of 9 mod 11? Yeah, 5 times 9 is 45. That's one more than 44. What about this one? We'll end with this one. What can you multiply 4 by to get 1 mod 6? 1 times 4 is 4. That doesn't work. Okay? Turns out you try all the possibilities, an inverse does not exist. So sometimes an inverse does not exist. And that's true of integers as well. 0 doesn't have a multiplicative inverse. Here's a quick preview. An inverse does not exist if the GCD of these two numbers is not 1. So the GCD of 4 and 6 is 2. They don't have an inverse because of that. All these other pairs have a GCD of 1. So sometimes, so the answer is just that it does not exist. All right, we'll look at an algorithm for this next time.